All right, guys. So, morning again to everyone. So we'll start the class by looking at a particular question. We know we have been discussing a whole lot of things so far as it relates to radioactivity, right? We looked at different equations and all of that. We looked at stuff related to activities, and to better a better way to start the class is to just run a question to see how we go about applying all of this information that we have been absorbing so far, right? So that's what we're going to do right now. And it starts off by saying you can take on the question. It says that uh, radioactive source contains 7 times 10 to the sixth radioactive nuclei and has an activity of 4.5 times 10 to the 7 becquerels. Now it says for this source, they want us to calculate A, the decay constant, B, the half-life, and C, the time taken for the activity to fall to 2 times 10 to the 5 becquerels, right? Anybody can suggest what we're going to do here or how we can approach this question in terms of starting off by finding the decay constant? How do you think we can go about doing that?
So A equals negative lambda n.
Precisely. A is equal to negative lambda n. All right. Now, the question gave us some information. What and what did the question give us that we can put in here?
The number of nuclei.
The number of nuclei. Okay, good. What is that? And they also gave us the activity. I think we can clearly see that. I want to point out something to you. You see, if you're seeing radioactive nuclei and maybe in another question you see radioactive atoms, it's the same thing. All right. So if you see radioactive um, atoms and radioactive nuclei, they're talking about the same thing. All right. So in this case, we can ignore the negative sign for this one, right? And just go ahead and transpose the equation as such to find the decay constant. So our decay constant for this radioactive source is going to be,
I don't want to ignore next time.
yeah, the negative sign just signifies that the sample is decreasing. You understand? So that is the reason why we're going to ignore it in this case. Because the decay constant is not a negative number per se, right? And if you looked at the equation that I gave you yesterday pertaining to its activity, I did not include the negative, right? So the negative can be there, but as we said, the negative is just showing that the activity of the substance is decreasing. That's just the main reason for it. Good. And so we'll just go ahead and put it in our calculators to say, 4.5 times 10 to the 7, divide that by um, the number of nuclei, which is 7 times 10 to the 16. Somebody go ahead and divide up that and see what we're getting as it pertains to that. What are we getting as the answer? All right, let's confirm. Anybody else get the answer that can send it to me as well?
Again, sir?
I'm asking for someone to just confirm. So I want somebody else to send me the answer so I can see what the answer is.
Sir, I got 6.4 times 10 to the minus 10.
Minus 10.
Same, sir.
Okay. All right, good. I'm just seeing if there's a unit attached to the decay constant. The unit is, let's just check if there's a unit attached to it. Sometimes some constants have a unit, so I just want to see if it has any units. It would appear, I don't know if this book is correct, honestly. I think there's an error right here because there's no way you can, because remember that we can find the decay constant by saying ln2 divided by the half-life, just for argument's sake, right? Our unit in this case would have given us per second, so it means therefore that this thing is going to have a unit of per second. The book showed me something different, right? But I'm assuming that it has to be per second. Okay, so that would be the unit for this thing. So now that we have that, right, we can now go ahead, you see, and find the half-life. So we found the decay constant. So we can write it here to say our decay constant is 6.4 times 10 to the minus 10 per second. Now they want us to find the half-life, right? So the best thing for us to do is to just use that equation that I just wrote a while ago. To say that our half-life is equal to ln2 divided by our decay constant. This is how we go about doing that. So just a while ago, what I wrote was the one that we could use to find the decay constant. You just simply transpose to make the decay constant become the subject, right? So in this case, we just rewrite this. We know that this is a set formula that we can use whenever we want to find the half-life, right? Provided that we know the decay constant and we don't have a graph to match it up with. So having said this, we can say that our half-life now is going to equal to ln2, which you will see it written as, if you put it in your calculator, you're supposed to get 0.63, something of that nature, or 0.93, something of that. So ln2, let's just check what ln2 is. 0.693, right? So in some cases, in some books, you will see them saying that the half-life is equal to 0.693 divided by the decay constant. It's just the same thing as saying ln2. So if you see that somewhere, it doesn't affect the price of rice, right? And don't be confused, it's just the same thing. So we're dividing that now by our decay constant, which is 6.4 times 10 to the minus 10. So in essence, we're saying 0.693 divided by 6.4 e to the minus 10, right? For this, it tells us that the half-life is going to be a lot of numbers here. So this is 1, 2, 3. So it's going to be 1.08 times 10 to the 9 seconds. This is our half-life. Do we agree? Let me know if you guys agree.
Yes, sir.
Yes, sir.
All right, good. Then now, another part of the question now would have asked us to find the time taken for the activity to fall to this amount, right, in terms of becquerels, of course. So this is the unit for activity. So remember that the unit for activity is becquerels. All right. So the equation that we would have to use here is that exponential equation that says A is equal to A naught e to the minus lambda times t. All right. So we would use that to find the time here. So we're trying to find t. Now remember that A naught is the initial activity. The question gave us the initial activity. Good. And so they gave us the final activity as well. So we can pretty much do the mathematics to find out that information that we need. So let's go ahead and take it. So having said all of that, we can put in the information to say that our remaining activity is going to be 2 times 10 to the 5 becquerels equal to the initial amount, which is 4.5 times 10 to the 17 e to the minus our decay constant, which is 6.4 times 10 to the minus 10. And then now that's going to be multiplied by t, which is what we're trying to find. So what we could do here is to pretty much divide both sides by our 4.5 times 10 to the 17 on both sides to just make it look a little bit better. Right, we could go ahead and do that. Or we could have, I'm wondering if, we're going to try 2 ways and see if it's going to affect the price of rice, right? Because we could have started out by ln in both sides to just get rid of the e and all of that and so forth. But we're going to see and we're going to try it this way and then we'll see what happens. So this, we know, so this and this will cancel out. So let's just divide that and see what we're getting. So 2 e to the 5 divided by 4.5 e to the 17. I think I'm getting 4.4 times 10 to the minus 30. That is now equal to e raised to the minus. I think you see, we don't do it this way because you see this minus sign needs to get cancelled and it now will get cancelled so easy. If
Sir,
oh yes, go ahead.
sir, you have 17, it's just 7.
So you say it again.
4.5 times 10 to the 7. 17 here.
You sound a little bit low. Give me a second. Go ahead now.
I was saying, sir, you have 4.5 times 10 to the negative 17 is just 7. 10 to the 7.
You mean right here, sir?
Yes, sir.
Isn't it? It's plus 17, right? Plus 7 or plus 17? Or plus 7? Oh, I see.
7.
7, I see. All right, thanks. All right, guys. I think the way I'm doing it now could work. So let's just try it and see. Because I just realized that we might get the negative number to cancel out. So it's 7. All right. So when we do that now, it is. So this is gonna be 4.4 times 10 to the minus 3. Okay, let's see here now. Right, so the next thing that we will do here is to ln both sides, right? So pretty much we're multiplying both sides by ln. Just to cancel the ER to take this thing in the power and bring it down. That's the whole essence of doing the ln scenario here. When I ln 4.4 6.4 times 10 to the minus 3, I am getting minus 5.4, right? 5.4, and of course that is now going to equal to minus 6.4, right? Times 10 to the minus 10 times t. We can go ahead and divide both sides by the minus 6.4 times 10 to the minus 10. Right? So when we do that, we have minus 5.4 divided by minus 6.4 e to the minus 10, right? We're getting that the time here, this time t, is going to be a value of, 8.4 times 10 to the 9 seconds, right? So we can see that this is what we're getting here. All right. I wanted to try it another way, but I think we might get back the same answer. I think we might get back the same answer.
Sir, how did you get the 4.4 times 10 to the negative 3?
We divide 2 times 10 to the 5 by 4.5 times 10 to the 5. You didn't see that part? You see it now?
Sir, divide it by what? 4.5 times 10 to the 5?
No, to the 7, which is the activity, right? That's the initial activity. So we're dividing the final activity by the initial activity. Because remember, the equation says that A is equal to A naught e to the minus lambda times t, right? So all I did was to take this initial activity and divide it by the final activity. So that's what you're seeing here.
So the answer is supposed to be 4.5, not 4.4.
What you did? You round up or something, or what? I don't know. Is that what you did? Let me try it again.
Wait, never mind, sir.
Oh, okay. Right. So yeah, I think this can work. This method could work. But what I wanted to do, I wanted to, like, ln both sides first, right? And then, which should have basically pencil back out to be the same thing. And then I would have expanded right here. So I would have had ln a naught, right, plus ln e to the minus lambda times t. Cool. This is equal to ln a. Ln, all right, I don't have enough space. And then I would just, because we know that ln a is adding on this side, then you would bring it across and it would subtract. So let me see if I can write somewhere else. It should give us the same answer, but we just want to confirm. So we're now saying ln a minus ln a naught is equal to e, well, not e, but minus lambda t. When we do this math, what would be ln a? Ln a is what? Let's try that. Ln of 2e to the 5, that gives me 12.2 minus ln A now, ln A naught I should say. So ln of 4.5 e to the 7, that gives me 17.6. Let's find the difference there. 12.2 minus 17.6, I got minus 5.4, which is now equal to, the minus 6.4 times 10 to the minus 10t, right? So it could have gone both ways, because at the end of the day, I seem to end up back with here. So you understand? So the order don't really matters in a sense how you go about doing it, but you just have to just ensure that you're maintaining, what you need to maintain. You have to ensure that you have to ln at some point. You could have ln first, right? And remember now that that whenever you ln the entire thing here, you are actually you can split it apart by saying you're adding, because you're multiplying these two things. You're multiplying ln A and E to the minus lambda t. So you would have to split that in by saying ln A plus ln E to the minus lambda t, which is just talking about the laws of log. So we have to remember the laws of log in this regard, right? So I think we're through with that that question. If you have any concerns or any comments, you can let me know from now. Now things are going to get a little bit much darker for the next questions per se, right? But let's see what is taking place here. Right, this one is going to involve a lot more stuff that you have to remember mainly, right? Especially when you see a question like this. So it says that sodium 24 is a radioactive isotope with half-life of 15 hours. Now it says a pure sodium 24 has a mass of 5 grams. First, they want us now to calculate the number of sodium 24 atoms present in the sample, right? Which is basically your n value that you want to find, right? The number of nuclei per se. And of course, they want us to find the decay constant, the initial amount, the initial activity of the sample. It's supposed to be sample, right? And so forth. Now, how do you think we're going to find out the number of atoms, right, in that given amount of sample of sodium 24? By the way, sodium 24 is an isotope, right? And isotopes are generally the ones that undergo radioactive decay and so forth. So you have to also remember that. So we'll look at how we use these in different industries and all of that. But we just want to take this question, all right? Anybody have any idea as to how we're going to approach it? Have you ever heard about Avogadro's constant before?
Yes, sir.
Yes. All right. Yeah, we'll have to use that number here, because what that number tells us, it tells us the amount of atoms, within a particular mole of a substance, right? So one of the first things that we can do here is to find out the amount of moles that are in, this particular amount of mass of sodium. And for the chemistry persons, I really don't like chemistry, right? So we could go ahead and say, all right, let's find the number of moles. How do we find the number of moles?
Mass over molar mass.
Yes. So mass in grams, right, divided by the molar mass, right? So in our case right here, we have it that the mass in grams is 5 grams, and the molar mass is 24, which is given to us. So by dividing up this, we can find out the amount of moles that are in this element, but that does not tell us the amount of atoms as yet. So we have to do another calculation. So we're dividing 5, you know, by, let me just check something here. What are they doing here? All right, we're going to try it this way and see what happens. I don't know what they did right here, but let's see. So we're getting that the number of moles is going to be 0.21 moles. We can write it as such, right? But we have to now remember that in 1 mole, there is 6.02 times 10 to the 28 atoms inside of it. All right. Let me just confirm something here. Okay, yeah. So now, if we know that in 1 mole there's this amount, right, of atoms, of the sodium atoms, then now, in order for us to find out the number of, pretty much the number of nuclei in this 1 mole, I have to go ahead and times this number, this Avogadro's constant number, by the number of moles to find out the number of atoms that are pretty much present inside of the inside of that particular mole of the sodium atom, right? So let's see if we can do that. So if we go ahead and say 0.2 moles times 6.02 times 10 to the 23, right? We are getting a number that says the number of atoms, right, that is contained in 5 grams of the sodium is going to be 1.26 times 10 to the 23rd power. And as we said, that this is the number of atoms, which in a sense is the same thing as the number of nuclei, so to speak. So for that now, we can say that this is the amount of N value that we are starting out with in that given sample of sodium atoms. So just always remember now that you have to kind of like do this conversion. If they give you like the mass and all of that, right? You have to then convert it over to find out that overall number of nuclei. So just remember that this is Avogadro's constant. And by the way, your constants are given to you. Your constants are given at the front of every exam paper. So you don't really need to swap the constants. You just you need to know the basics, of course, like maybe the speed of light, even the one for the electron, they give you that as well. They give you the mass of the electron, mass of the proton, those things. So you don't need to swap those, right? But you just really know when to use them. That's all you really need to know how to do. And I think they give you Avogadro's constant as well, right? if you are given questions pertaining to this. So now that we have that, right? And by the way, this whole concept of Avogadro's constant was derived from, carbon 12, right? Was derived from carbon 12. But I will restart the session. I have less than a minute. I'll restart it and then we'll pick up from there. All right. Let me see your percentage. All right. Okay, now. So next part of the question is asking us to find the decay constant, right? Now, how are we going to find the decay constant, guys? Let me hear what you have to say about that. Hmm? Yes? Anybody? How do you think we can go about finding the decay constant? Anybody want to give it a try? Decay constant? Come on, guys. How can I find the decay constant here? What information do I have that can give me, the value of the decay constant? I wonder if you guys are in the class, if you are not. Huh?
Sir, the change in N over the T, the time. Okay.
Changing what? I didn't get that.
A change in the quantum nuclei. I don't know.
Remember, what is the decay constant? What is the decay constant?
Sir,
Go ahead, please.
sir, the decay constant is lambda, so would we use like the ln2 over the half-life?
Precisely.
Okay.
Precisely.
Okay.
Right? So, decay constant, because you have to remember that there's a relationship between the decay constant and the half-life. So we could write, so at first, if you know that the half-life is given as ln2 upon the decay constant, you can transpose to get the decay constant. The question gave you the half-life, right? So it means therefore that you know what you need. You don't have the activity, so you couldn't go ahead and use the activity equation to find the decay constant. So you would use this one to say that ln2 upon the half-life. And this is where now it kind of gets important for us, right? We have to convert the time that is given. So if the time is not given in seconds, we have to convert that hours, or even if it's days or years, we have to convert it into seconds, because as we can imagine that the decay constant has a unit of per second, right? So we have to maintain that parameters for the most part, right? So as you can imagine, you know, in how many seconds are there in 1 hour? Or we don't have to do it that way, but we can say, all right, how many seconds are in 1 minute? We know that that's 60, and there are 60 minutes in 1 hour, so we can say 60 times 60 would tell us the overall seconds in 1 hour. I would just multiply that number now by the 15 hours to find out the total number of seconds. Do you guys follow? So we are converting hours to seconds, right? And we know that in 1 minute, that is 60 seconds. In 60 minutes, is that what I need to say? Let me check. Yeah, so to find in 1 hour, let me just rewrite that. Let me just rewrite this. So yeah, so 1 minute is 60 seconds. 1 hour is 60 minutes, and we know that 1 minute has 60 seconds. So to find 1 hour in terms of seconds, that would be 60 times 60. So in 1 hour, you have about, 3,600 seconds. So if we have this amount in 1 hour, then in 15 hours, we have to then multiply that by 15 to find out the total amount, right? Which should give us a value it should give us a value of 54,000 seconds. So let's look at it. 15 times 60 times 60 is going to give us 54,000 seconds. So having said that now, what we now need to do is to go back into this equation here to find our lambda. So 0.693 divided by 54,000 seconds will then tell us the decay constant, 0.6 93 divided by 4, 40, 54,000. 54,000. So I'm getting that the decay constant has a value of 1.28.
Sir, how did you say you calculated? Oh, never. Sir, what did in the denominator is T, and at the bottom we have a half?
Yes, because that is the symbol for half-life. Yeah. So this is what I'm getting for my decay constant. 1.28 times 10 to the minus 5 per second, right? So having said that, I think we can now go to answer the next question. All right. I believe we can go and answer the next question.
Sir, and how did you say calculate the half-life?
The half-life? What do you mean? Like you don't remember the formula to find the half-life? That's what you're saying?
Sir, I saw you doing something, sir, with some. Sir, I saw you converting how much hours, how much seconds make an hour, but after that, I don't know what you did
Okay.
or why
Okay.
you were doing it.
All right. So what I was saying is that in order for us to find the decay constant, right, we have to convert hours into seconds. So remember, our half-life is this amount, 15 hours. So we should convert this 15 hours into seconds, which is what we did to say that if in 1 minute you have 60 seconds, then in 1 hour you have 60 minutes. Then in total, in 1 hour you're going to have 3,600 seconds. And if your half-life is 15 hours, then you're saying 15 times that 3,600 seconds to give you the half-life in seconds. You get me?
Yes, sir.
Yeah. So that's what we did there. So we have that now. We know our decay constant. The next part of the question would ask us to find the initial activity of the sample, right? Just be mindful that this is supposed to be sample. So the best thing for us to use is that equation that says A is equal to, we could say minus lambda times n, but as we said, the minus sign really just show that it's going to decrease. So we could just write it as this without the minus sign, and it wouldn't affect anything. So all we're going to do now, we know all information. We know the initial amount of the atoms that are present, and we know the decay constants. All we're just doing is some mathematics, and we'll just get our 2 marks and we're going about business, right? So let me rewrite that. 1.28 times 10 to the minus 5 times the number of nuclei or atoms that we have, which is 1.26 times 10 to the 23rd power. When we do that, we find the activity now, and we should be getting a number to say that the activity, which is A naught, by the way. So by the way, this is A naught, so just be mindful, it's the initial activity. So A naught is now equal to pretty much 1.6 for the most part times 10 to the 18th power. And now is where you write the unit becquerel, right? That is now is when you write the units becquerel. Good, and we have that now. Good, we have that information now. So that's the initial amount that we start out with. See? So the question could then go to ask us to find the activity of the sample after after 45 hours. So they want us to find the activity, which is basically the remaining amount of the sodium thing, you know, after that amount of half-lives in a sense, or you know. So one easy way we can do this is to remember that whenever a half-life occurs, that speaks to the time taken for half the initial amount. Is that how it goes? Let me see if I can see that properly. So the half-life speaks to when the given amount is reduced to a half, right? So if we know that the half-life is 15 hours, and they are now asking us to tell, or they're asking us to determine, you know, the activity after 45 hours, I think we can go ahead and do that simply because in 45 hours, we would have had a total of 3 half-lives, right? So we expect that the initial amount that we have, which is the 1.226 times 10 to the 23rd, is going to halve itself 3 times, right? To basically find the remaining amount, so to speak. But we could even use the formula to just make it easier for us if we don't want to do that. But at first, we're going to just use the concept here. Let me just show you what I mean. Let me show you what I mean. So remember, if we're starting out with this amount, we'll start out with 1.2 6 times 10 to the 23rd. Obviously, the time here is going to equal to 0 hours. All right. Now, in 15 hours, we expect that this initial amount is going to be reduced by a half. So we could just say, all right, activity divided by 2. Initial activity divided by 2. And when we do that, you would essentially be saying 1.26 e to the 23rd divided by 2. We would get a value to say, you know, 6.3 times 10 to the 22 atoms in a sense, right? Then we could do that again. We could find the next half-life, which in this case is going to be 30 hours, right? Because remember, we say half-life is constant, so it is, you know, the next half-life would be the next 15 hours, which is in this case going to be 30 hours. So we want to see how much is remaining now. So we're taking this amount, which is the 6.3 times 10 to the 23rd, and dividing that by 2. When we do that, let me just assume that this is, hold on. 1 second here, guys. Yeah, we're gonna see if this is what it pans out to be. Let's just confirm and see. So this is going to be 3.15 times 10 to the 23rd. Let me see here if it's going to give us. No, let's not take it this way. All right, it's not going to give us. It's not going to give us the answer. It's not going to give us the answer using this method, right? Yeah, it's not going to give us. Let me, I did something wrong, you know. I used the wrong information. I supposed to use this. This is what I'm supposed to use.
Sir.
Yeah, go ahead.
Yeah, why did you use 1.26.
Yeah,
Yeah.
I just realized that I used the wrong thing. I used the wrong thing, man. I just realized.
Uh,
So it's not n that we are using. Sorry about that. Right? It is a naught, which is the activity. So it based on the answer that I'm working towards, I should get it now. Um, so we know we started off with 1.6 times 10 to the 8. Then now for the second half life, that is going to reduce by a half. So more than likely it's going to give us the answer that I want now. Divide that by 2, right? This are going to be basically 80 times 10 to the 6, which we could have said 8 times 10 to the 8, right? And I believe we're going to halve this again. So if we halve this again, let's see. All right. I doubt this method is actually working. I doubt it's working. Is it working? Let me just check. All right. So the next one is going to be 4 times 10 to the 8. Yes, yes. I think it's working. No, it's not working. I'm doing something wrong. I'm putting in the wrong information, man. It's supposed to be 18 here, so. I keep putting in the wrong information in the calculator. All right. Let me try it again. All right. So yeah, we'll get the answer now. I'll just keep putting in the wrong information in the calculator, guys. Sorry about that.
Sir,
Yeah, go ahead.
sir,
Yeah, man.
wouldn't the 1.6 be at 15 hours?
No, it wouldn't be at 15.
And then
It wouldn't be at 15. Y'all get me? Because what you have to understand when you say,
okay, so
so if you say the initial activity, right, that is when no time has lapsed as yet. You understand? It hasn't started decaying as yet. The only so as soon as you start the time now, right, and you reach 15 hours, that is when you would record your first half life, which is half of the initial amount, which in this case is going to be 8 times 10 to the 17. I was doing a little bit of craziness with the maths right here, so sorry about that. So now the next one now should be 4 times 10 to the 17. Then the next one, which is going to give us 45 hours, which is the third half life, is going to be 2 times 10 to the 17. This is what I wanted to get at, right? But I kept mixing up some numbers here, right? So this is the amount that is now remaining at 45 hours. We could have done it a different way by using the equation that says A is equal to A naught e to the minus lambda times t. So initial amount would have been 1.6 times 10 to the 18th, right? E to the minus 1.28 times 10 to the 5 minus 5 rather times the time. So we could convert this 15 hours into seconds, which is not 15, by the way. It's 45 seconds into seconds, 45 hours into seconds. That's going to be 45 times 3,600, which I will give us 162,000, right? Let's work out the top part here. So 162,000 times 1.28 e to the minus 5. We're getting that e to the minus 2.07, right? I will put the number in front. Let's work out the e to the minus 2.07. When I do that, I get 0.12. Let's just put it at 0.13. I'm going to multiply that now by the 1.2 times 1.6 times 10 to the 18th, and let's see if we get the answer. Oh, right. So it gives you a much refined answer in a sense. It gives you a much larger decimal point, but at the end of the day, they are the same thing. This is somewhat more accurate to use. So I'm getting 0.28 times 10 to the 15 becquerel. Right? Let me hope you guys understood what we did here. Are we seeing what we did here? Let me know. Come on, guys, talk to me now. Talk to me. Let me know if you guys comprehend. Let me not hear nothing from you guys.
We're here, sir.
All right, good.
Sir,
Yeah, go ahead, Dennis.
how did you get 162,000?
The one what? Yeah, man. The time.
162,000.
The time. Remember, we have to convert the time.
Is it 45 hours?
45 hours times how much seconds is in 1 hour. So we have to convert it from hours to seconds.
Sir.
Yeah. Mm. Okay. All right. Let's try this one for yourself. It says that you're gonna write this one for yourself now. The question starts out by saying a radioactive isotope has a half-life of 18 days. It has a half-life of 18 days. Full stop. We have that so far?
Sir, repeat, please.
So a radioactive isotope.
You can repeat, please.
Yeah, man, I'm
Repeat, please.
Yeah, I'm going to repeat. So a radioactive isotope has a half-life of 18 days. A sample of the isotope contains 3 times 10 to the 12 atoms. says calculate the decay constant of the isotope. This is 3 marks. Next part says the initial activity of the substance, or of the sample rather, which is also another 3 marks. Then the last part of the question says the activity. So they want us to calculate the activity of the sample after 72 days. Yeah? I want us to pay attention to these questions because let me know if you're finished taking down that. Please know how to do these questions. I mean, from all 3 questions that we have been looking at, right? I don't think it can become any more complicated than that. Just know the structure, know when to use the Avogadro's number. That is when you want to find the number of atoms within a particular mass of a substance. It's not in all cases you will use the Avogadro's number, because in this question you don't need to use the Avogadro's number because you know the number of nuclei or the number of atoms that is present, right? The reason why I stress these questions is because they're obviously on past papers, right? And I think this is one past paper question that involves a question of this nature, right? So it's of paramount importance for us to pay attention to it. So you could even take this one and try it for yourself just the same way, right? So it says that a radioactive sample contains 3.5 micrograms of pure carbon-11. It says which has a half-life of 20.4 minutes. It says determine the number of nuclei in the sample at time equals 0. They want you to find the time constant of the sample. They want you to find the activity of the sample at time equals 0, and also to find the activity of the sample after 8 hours, right? So, and you can see it's an 8-mark question. The chances are this probably value 2, 4, 6, 8, right? So, be mindful, guys. Pay attention to these things. So just take down those questions and solve them for me, right? Solve those questions. We have a lot more content to go through, but we just wanted to put in those things there so that you can practice.
Sir, which question should we start from?
The one that I gave you first, this one here. You wrote it down?
Yes, sir.
And then now, this one, this past paper, and you can see now, right now by time we don't finish, well, for those who are paying attention in class, we went through a lot of past paper questions already, right? We got through a whole lot of past paper questions. Because what I do, I look for the topics and I say, all right, let's do this question. Now, even some of the tests only get in a recent times, one or a few of the questions were possible questions. But you know, mean to say, for no more exam, you know, I get no passing of questions. You know what I mean? I might just build some questions for you guys.
No, sir. Please give us possible questions.
No, man. I mean, the thing is now, remember the case kind of changed in a sense, and we don't have much past papers again.
Let's come off of the ground.
How we are talking, Virgin?
Dog is on the ground.
Yeah, Virgin,
Come here.
mute the mic, brother. Mute the
What
mic.
is that for? Come here. Come here.
With our mother being
Huh?
sister. Yo, Dennis, are you babysitting, man?
Sorry about that, sir.
Are your son that? Are your daughter? Which one?
Son, sir.
Are your son? Oh, you're going to things, man. You're going to things, dude. That's what you
Yes,
have to
sir.
do. You have to do, you know?
Is it, sir?
You have to do, you have to do. If
That's
you have to
right,
make,
sir. That's right.
if you have to make youth, you have to make youth, you know?
Sir, question, sir.
Go ahead.
For C, the 11 over the 6 right there, sir.
Mm-hmm.
Is that the what that be again for the carbon?
Yeah, so the 11 is the molar mass, which is the atomic mass. 6 is the number of protons or the atomic number.
Okay, sir.
I think you guys probably should just take the entire number 6 question, right? As I said to you, know, like these questions were easy, you know, like this is an easy question, an easy 15-mark question to rock stone. Can you imagine going into an exam and you know how to define an isotope? You know how to find the number of protons, number of neutrons, right, and number of electrons in radium, and then you know how to define half-life and decay constant and write the equation that relates both of them. You see the equation that we talked about a while ago? That's the equation that you have to use here, so you know. So it is write an equation that relates the two quantities, which is half-life and decay constant. So remember, we say half-life is equal to ln2 over decay constant. That is what they ask you to do, right? So you have to be specific. You can't just give any random equation. You have to give the one that they asked it for. So you could easily get your 15 marks yes, if you know how to do all of this, yes, right? But as I say, key have changed, right? So I don't think you're getting a simple questions like them again, where you know you have to do these things like that. Let me just look at something here. Right, as it pertains to you know, these questions these days just require a lot more applying, you know, small concepts. You know what I mean? It's no longer like just giving us those simple type of things. And as I would have stated to you guys before, that don't neglect no diagrams that you are seeing. Don't neglect no diagrams. So I'll give you a few hints, you see, for your model exam that is coming up, right? If you things like Wheatstone Bridge, make sure you go back over those things, right? If you things like capacitors, make sure you go back over those things. And you know, talking about Coulomb's law, those things, make sure you know those information. You must know everything about not everything about capacitors, my bad, but even the very unit for charge, you must know to define that. Because keep have a way of giving you those definitions, right? So use the syllabus as a guide when you're trying to study for the model exam, right? Less than a minute, I'll restart. Take control here. Oh my God, I'm singing and I'm recording. I didn't even realize. Right? All right. Think you guys have probably screenshot this by now. So the thing I was talking to you guys about yesterday as it pertains to the exam paper. So this is a section B question. This is the last question on the paper. So module 3 questions. It's all about pretty much radioactive decay and so forth, half-life and all of that. We're going to scroll up back to this, the third question to just see what it's going to be about. It's going to be about a total different topic. See, this one now is on Planck's constant. Not Planck's constant, my bad. Photoelectric effect, I should say. So so this is related to photoelectric effect. It says name the scientist who is credited, right, with the explanation of the photoelectric effect. I wonder if we know that scientist, by the way. I wonder if we know his name. Bro, you're not supposed to be asking me this question because I sent some links in the group, right, that contains a lot of information pertaining to physics particles and so forth. But you guys are not looking at things where I send can give you. So even right now, me probably even send out the multiple choice so me I'll give up on the exam. And most of them probably not go through the group. This is yes, this is probably one multiple choice so we can start practice and this and that. Eventually we can force some little things, right? I sent some links in the group. Whenever think about clicking on it to see, all right, what it's all about, So that's all I've got to. Right. Photoelectric effect. Yeah, man, the file is supposed to be there now, right? The file is there. Once you have that file, you will see documents that have a lot of past papers, right? A particular CAPE document that have a lot of past papers in it. Honestly, these questions are not hard, you know. Like, I mean, come on. You can easily get a 1 mark question by just simplifying the frequency here, so, right? The guy who was credited for this experiment is Max Planck, right? He's the one who got credited for this. There are other scientists who did work, but Max Planck was the one who got credited for it. And also, you could even take into consideration even Einstein as well. Einstein, you know, did some amount of work as well. So this question is kind of twofold, but I think it's mainly it could be Max Planck, and it could be Einstein. So they want is with reference to the photoelectric effect, explain the threshold frequency. Yes, with reference to the photoelectric effect, explain the work function, right? You see, all diagrams like these, back in the days, they would ask you to draw stuff like these or to label it and all of that. You see what I say? So I think you should not neglect these diagrams that we look at sometimes. Simple graph they're going to ask you to find. I want to emphasize something. I know it's not you guys, but like some lower six students, they don't understand, or they're not trying to see or to use their brains a lot to see that whenever they tell you to plot a graph of something versus something, the first thing that is stated, that is what goes on the y-axis, and the other thing goes on the x-axis, right? So in this case, if you're going to plot the graph, you're expected to plot stopping potential energy versus frequency. So you have the stopping potential already, but you don't have the stopping potential energy. What you need is to times that by E, that is the stopping potential, but you need to times that by the charge of an electron to get the overall stopping potential energy. So those are some things that you have to really kind of pick up on. Then they want you know, if you like the same lab we are doing right now, or someone I fill up on yourself all about, right? This is kind of like even a general passive question related to all of this. So if you don't understand the lab, you know, then chances are you're going to exam and see a question like this, it's going to eat your supper. It says, you know, and it says, when it says using the graph, these are some of the questions that you guys overlook sometimes. Some of you will just use the equation and solve Planck constant, which will run into problems. It's a 4-mark question, and I don't understand sometimes when you see a question and it values certain amount of marks, that will tell you how much amount of work you have to put in to get the answer. You can't just take the equation and just put in 2 numbers and expect that value 4 marks. No, in this case, to get Planck's constant, you have to go find the gradient. You understand? So probably 2 marks out of that have to find the gradient, and probably the next 2 marks is for you now to compare to say the equation, that linear equation that Einstein came up with, would now show us that the gradient is corresponding to Planck's constant and all of that. The question also went on to say that using the graph to determine the work function. So if them tell you to use the graph, you have to use the graph. You understand? These graphs are tricky graphs because how the graph is supposed to look. Yeah, so it could be Albert Einstein. Yeah. So for this one, it's Albert Einstein. So I said it could be 2, but it's Albert Einstein. We're going to stick with Albert Einstein, right? Because that equation is more defined, you know, more acceptable. Let me see. I think I did show you the graph already, but let me just show you again how the graph is supposed to look like. EVS versus frequency. Hopefully it will show me. Cause some of you don't think, you don't think sometimes, and that's okay. That don't affect me by much, right? But you see this graph here, so this is kind of like how even your lab's supposed to even look in a sense, right? I might not penalize you a lot about this, but this is sort of like how the graph's supposed to look. You're supposed to have a y-intercept. Wherever you intercept with, so chances are that might be your work function, or you might have to use that to find the work function. You see what I say? So the graph's supposed to look something like this, where you extrapolate it, right, to come down to this point. And none of you probably say, you never say, make you go and research it to see if it makes sense and all of that. You know what I mean? So like with a question like that now, you have to use the graph to find the work function, which is basically the y-intercept. Cool? So, the things are not hard, but it's just that someone just stubborn on themselves and don't listen sometimes, and don't try to research and actually find out some information on their own as well, right? It's more you have to understand that if you keep as well, it's preparing you for university because it's going to get even worse out there, right? And you have to develop that habit of reading for your degree. At this point, you're doing the same thing. You're reading for your CAPE results. You understand? Because pretty much CAPE is like pre-university. So when you go to university, you're doing some of the same things and adding more information to it. So it's pre-university level you're at. So let's put this in the back of your mind somewhere, right? Put this in the back of your mind. All right. You guys finished working those questions, by the way? Oh, by the way, these are the constants that I was talking about, right? These are the regular constants that are given to you. So you have to stretch yourself to remember the permittivity of free space or the permeability or those kind of numbers. You don't have to stretch yourself to remember those. All right. They give you Planck's constant as well, so you don't have to kill yourself. And see this information when you're trying to find binding energy and all of that. They give you what you represent, good, and they give you also what one you represent in terms of electron volts. They give you the mass of the electrons. They give you the mass of the protons. They actually tell you what acceleration due to gravity is supposed to be. So, yeah, they give you Avogadro's constant. Those are the general constants that they give you. They can add more to it if they see necessary, but these are the general ones. Anyways, guys, finish up those questions for me. I'm going to create a portal where you can submit the answers as well. All right. If you have any questions, go ahead and ask them now because I'm going to pretty much end the class now. All right. All right, that's it then.